Okay, I'm waiting for the recording to start. So I think, yes, the recording started. So let me summarize again. Today's topic is to implement ASCON. So ASCON won the competition, as I mentioned, NIST Lightweight Crypto competition, and the winner was announced in February 2023. And I always mentioned that the final standard is not ready yet. But just a few days ago, NIST published an initial public draft. So this is not the final version, so it might change at the end, but this is what they provided for the public. So I will try to implement this. Okay, so today we will try to implement this one. So as you can see, this is the NIST documentation. IPD means initial public draft. And it says Ascon-Based lightweight cryptography standards for constrained devices, authenticated encryption, hash, and extendable output functions. So this document actually includes a lot. So let me go a little bit further, and there is an important, I recommend you to read everything, but there's an important stuff that is mentioned here. So also let me go to index, table of contents, and as you can see, here it talks about Ascon permutation, then starts talking about Ascon-AEAD128. So this is the thing that we are going to implement, okay? And as you can see, there are parts where you see encryption, decryption, etc. So a hash function is also here. So, but we are not going to implement that. So I mentioned this 128-bit stuff because there is this part says differences from the Ascon submission version 1.2. So in my previous implementation, I actually focused on Ascon submission. And in the Ascon submission, there were actually two variants. So they were Ascon and Ascon 128A, as you can see. So the rate and capacity were different in these cases. And there is also one version, ATPQ, which was a version that is, just for the post-quantum cryptography. But this document says that this standard specifies the Ascon-AEAD128 algorithm, which is based on Ascon 128A. So this is the difference. So in my previous, in the lectures and in my implementations, I always focused on this version because we thought that this will be the one that is going to be standardized. But it looks like NIST is going to standardize this one and modify it with this name. So we will implement this one, okay? So before implementing, let me see if our Visual Studio works correctly. So I will simply include standard libraries, standard input output library. Okay, so start with the main function and say print the hello world. Okay, and let's see if it works. Okay, so maybe this void and do not return anything. So let me first compile. This is for the sanity check, and it failed already. I forgot the /n here. Sorry for that. Yes, if we run it, it says hello world. So good. We are good to go. Okay. So let's go to document and see actually what we are going to implement. Let me go to the big picture, which we always focused on so far. Okay. So here it explains parts of Ascon, but then here's the part of the main picture. Okay. So as you can see, there's an Ascon permutation which is run 12 times at the initialization part, and it takes IV, key, and nonce as the internal state. And recall that our internal state was simply 5 rows of 64 bits. So let's start implementing these first. Okay, so first I will type def. Since we are going to work on 64 bits, I need an unsigned variable for this. So the unsigned long int actually is referred to like this in Visual Studio. It is unsigned long int, most probably in many other compilers. And I will simply name it as bit 64. Okay, so I would like to refer to is yes. Okay, so whenever I say, for instance, here, I will say bit 64 x5. This will create an array of 64-bit values of 5 variables. Okay, so let me erase this one. And it is always good to initialize everything to 0 if it's not determined yet. So recall that we will have an IV, which is also 64 bits. Okay, so I will write it later. We will need key values, which is 128 bits. So I will simply refer to as key 0 and key 1. So we can also type them as 0, 0. And we will have need a nonce, okay? 64 nonce, which is also 128 bits, okay? And simply write this, right? So let's initialize everything to 0, then we can modify it as we go. Okay, so recall that these values will be fed into the internal states, and then, we will apply the permutation. So initialization phase actually takes these values, right? So we need an initialization function, right? Initialization. Which simply takes these inputs, which are, the R states, IV, key, and nonce, right? And of course, since there is no such a function, if I run this, I will receive a runtime error. So I define a function, initialization, like this. Okay. And it will take input like bit 64, sorry, of an array. In the past, you need to specify the sizes of the arrays, but now you don't have to, so we can simply write 5.
Yes, sir. Sir, please, can you increase your screen? Yes, go. Yeah, thank you.
You're welcome. Okay, so it will take IV. I don't know why there is an error here. Okay, about the titles. So we haven't finished writing it yet. So it will take bit 64 as key, and also bit 64 nonce, okay? Which is also, I mean, you don't have to write the array sizes. It will take them as input, but, to avoid wrong memory accesses, it is generally a better idea to write it. So if you don't write the initialization, I mean, what we do inside, this is referred to as actually declarative programming. As you can see, I started the writing as the main function. Then I realized that I need to do the initialization, right? Simply, I call a function named initialization, and I simply claim that there is a function as initialization, but I haven't written it down yet. So this is called declarative programming. You actually declare as if something is there. So actually, for instance, it is done. It does the initialization, right? I mean, because you call it. All I need to do is now write what the initialization does. So actually, if you recall, let's go to the document and see that the initial state is first 64 bits is IV, following 128 bits is K, the secret key, and the following 128 bits are the nodes. So you need to write it like this. So X0 must be the IV, right? So X1 will be the first part of the key. So key 0. Then I copy this because it's 2. You should always be, of course, careful when copy pasting stuff. in C programming. But anyway, next part is nonce. X3 will be equal to nonce 0, right? And X4 will be nonce 1. So now we have done the initial part of the initialization. If you go back the picture now, what we need to is to perform the ASCON permutation 12 times, right? So actually, let's say that there is a function called P, and we run it for 12 times, right? E is less than 12. E plus, okay? And we do the permutation, right? So permutation needs to be applied on the internal state. So I will send X as the one of the parameters to this permutation. So I don't know if I need to add any other parameter. So again, this is the style of declarative programming. I call the permutation P, but actually I don't have it yet. So I go again upwards and define the permutation P. So currently it simply takes the inputs 64x5. So I will determine if in the future I need anything more. Okay. So as you can see, if you compile, actually I should compile from time to time to see if I do any mistakes. So the compilation is successful. Apparently I didn't do any programming error, but currently actually this doesn't do anything, right? It does the initialization function and it runs the P function 12 times, but the permutation, the P function is not there yet. So we have to implement it. So we have to go and see what is done inside this P. So recall that this is inside the document defined like this. So let me go upwards. Yeah, ASCON permutations. As you can see, it performs first constant addition, then substitution layer, then the linear layer, right? So let's start with the constant addition. Okay, I think, yeah, in the official ASCON document, the rows were referred to as X0, X1, X2, and I think in this document they are referred to as S, but it doesn't matter for us, okay? So, constant addition layer, it says that there is a table here, and the constant is added to the second row. In our case, it is X2. So this is the list of constants, okay? So I have to copy paste everything. So as you can see, this is just 1 byte. And this looks a little bit different than the original ASCON constants. But anyway, you have to do this one, right? So I will copy paste because there are 16 constants here, probably for some specific reason. So I'm just thinking how to copy paste it as the easiest way, okay? Let me do this first and see how it is copied here. Okay, actually we received them as you can see like this as the value. So let's say that I have constant C of 16, let's say, and they are defined like this. So I have to put a comma between all of these values so that the compiler is happy. Okay, so let me press enter here to fit it in the screen. Yeah. And this, I guess. So yeah, I think we are done. Okay, so but which constant you are adding actually depends on the which round you are, right? So for this reason, when I call the P permutation as an input, I should also send the number of rounds I'm in, right? So this way it knows which value to add. So I will also take an integer I. We can name it a different way, but that integer will be added. So I need to check if we add this one at the 0th route. So let me quickly check the document. Generally, it says what it is. Yes, 16 minus runs plus I. So we have to understand this first. So let me see if initially it adds this one or this one. The constant Ci of round I of the permutation Ascon P round instantly with R round. So okay, so this is R&D is the number of runs that we are going to run Ascon. So in our case, the initialization runs this one with 12. So our variable R&D is 12. So it says that the constant 16 minus 12 plus I should be added. So it will be actually here. I need to also add another value 12 because I'm going to run it for 12. So this will be int R&D. So x2 is XOR. This is the XOR symbol, by the way, in C. With the constants 16 minus R&D plus R. Okay. So this is the constant addition. Okay. And then we need to do, so this is done, by the way, this is the constant addition layer. It simply does this. Okay. So next step is the perform SBox operation on every column. So this is the tricky part because recall that we are actually keeping our variables internal state in X5 as 64-bit values. So if I try to put 5-bit input to the SBox, I need to, for instance, take the leftmost bit of X0, then X1, X2, X3, X4, which is very tedious, okay? So in order to avoid this, in the original documentation of Ascon, they say that there is actually the algebraic definition of this SBox, where you define it with the 5-bit input and provide the 5-bit output by introducing logical operations with the input. So let me check if they also added this document, or we need to go to the original Ascon documentation for that. So let's see. Because then I need to cheat and, copy paste it from the other documents. Okay, from this document currently I cannot see if there is such a thing, but let's see. Okay, apparently it is not included in this document. So let me show you what I'm trying to do with our code. Okay. Oh, yes. So this is Ascon SBox. As you can see, it takes 5 bits input and provides 5-bit output. So if I implement this, as I mentioned, it will be very hard for me to get all of these values and perform 64 different SBoxes. But this SBox is actually logically defined like this. So for instance, the SBox takes 5 input bits, right? These X0, X1, X2, X3, and X4 actually are not the rows. They are simply bits. And the SBox operation actually performs this XOR and operations for multiplication. And for instance, there's an XOR with 1, which is not operation, etc., and provide 5-bit output. So if you just implement this line, all of these operations, instead of this table lookup, you end up with the same results. But the good thing is that if I do this operation not on bits, but rows, as we do as X0 and X1, then I will be performing the SBox operation in parallel 64 times. Okay, that is the thing. So these operations actually in the past we copy pasted it from another document in the ASCON submission version 1.2, and it works like this. So these are, I first defined 5 temporary values. For instance, it starts with, as you can see, x0 XOR x4. So let's go to the document. As you can see, x4 is XOR to x0. And you know, x1 is XOR to x2, etc. So all of these operations are summarized here. So if I'm not mistaken, there are 22 operations, maybe 23, I'm not exactly sure, but all of the SBox operations are defined like this. So again, if you define this x0, x1 as a single bit, this will perform a single SBox operation. But our variables are 64 bits, so actually with these lines of codes, we perform the SBox operation 64 times in parallel. So again, I copy pasted this from the ASCON documentation in the past. So if you also want to do that, you can simply go to ASCON submission. I mean, you can go to NIST website for the competition and find the ASCON submission version 1.2. Actually, it is included in almost every version of ASCON, and you can do these operations. So there's also one notation you need to know. For instance, here, in our constant addition, I wrote x2 equals to x2 XOR this value, right? So actually, if you are going to XOR something with itself and then write it to its own place, instead of writing it like this, you can erase this part and say that x2 XOR equals to this. So this is why all of these steps are defined like this. Generally, this gives you faster speed. So you should implement it like this if you want the speed. But if you don't implement like this, your compiler might turn it to this anyway if you allowed optimization flags. So generally, it doesn't matter much. But you know, to see a simplified code, this looks a lot better. So instead of storing the SBox like a table here and running it 64 times, we simply did this on 64-bit input, so we get rid of the SBox. So next step, diffusion layer. As you can see, we take the first row. They say S0, we say X0, it doesn't matter. You XOR it with 19-bit right rotated version of it and 22-bit right rotation of it. So this is actually like this. So X. So first, maybe we should define the rotation function to avoid writing it all the time. So we should define something like this, rotate right. It takes an input and a number of rotations we need to do. And we should define it like this. So X right shifted E times XORed or ORed with X left shifted, sorry, X left shifted 64 minus I times. Okay. Right. Let me see our previous code. So in the past, I used apparently XOR, not OR. It doesn't matter, but maybe for speed reasons, this might be the case. So with this in mind, so let me write this. So this is, by the way, constant addition. This is SBox. Now I'm going to write the permutation. So permutation means x0 actually equals to x0 XORed with x0 rotated 19 bits to the right. So rotation of x0 19, right? And if I recall correctly, it was also 28 times right rotated version of x0 right best. So let me go to the documentation. As you can see, x0, 19 bits and 25. So the other bits, so for this S1, it is S1 XOR S1 rotated to 61 times to the right and 39 bits to the right. So simply let's copy paste this. Okay. Again, copy pasting generally leads to error, so be careful when you're modifying it. So I will try to do it correctly. So this will be like this. I will look at the rotation numbers later. Let me first change the variables. So this was, I think, 61. And this one was 1. Let me see. Yes. 10 and 7. The other part is 39, 6. And 17 and 41, if I'm not mistaken. So let me compile it, by the way, and it looks correct right now. So actually, this is it. Now I also have the permutation. Okay. So let's actually do some sanity checks and try to print the results on the screen. So let me write a function called print states, which simply prints the current state. So for int equals to 0 is less than 5, since we have 5 rows. E plus simply printed in hexadecimal 0 x xi. So of course, as an input, we should take these x values, right? So this simply prints it on the screen, but when printing hexadecimal values, when there are zeros in at the beginning, actually when you print it, the compiler will show you only the non-zero part. So in order to fit the screen correctly, we should fill it with zeros when there are no, where the input part is 0. So let me do this. So let me print the states of x. So initially we filled with zeros, right? So this should print all zeros. So let me compile this first and run it to see if I'm doing correctly. So if there are 64 bits here, it should be 16 zeros. Then this should be the correct. So after the initialization, let me print it again and see if we are doing things correctly, right? Okay, so let me also give an, maybe we should put a okay, so since this is 64-bit, I think we should write it like this in Visual Studio. Let me compile it again. I think correct. Also, let me print out a ample line to distinguish the stuff. So let's compile it. And now it actually looks correct. If I didn't do any implementation error, when your IV key and nonces are all 0, if you run the initialization, which is 12 rounds of permutation, this is the result of your internal state. Okay, so I'm not sure if I did any mistakes so far. We can check at the end. And we don't have a test vector, by the way. So if I do an error here, and if we don't detect it, most probably we will detect it weeks later. Okay, so at this point, I don't know if I'm doing it correct or not. But it looks correct to me, so just believe me for a minute. Okay, so let's rehash. We started with this and obtain this, but of course, I mean, the key is our choice. I chose it all 0 just for simplicity. Nonce depends on us, but IV is actually fixed inside the document. So let's go to this document and find what is the IV. Okay, so let me go down. At one point, it should tell me what the IV is. As you can see, initial state is a concatenation of IV key and nonce. Okay, yes, IV is here. Okay, I will copy past this. Okay. So I will write it here. So maybe I should take this print state from here and print it before we do the permutation. Now if we run it, yes, this is the result. So IV is this. Keys and nonces are selected as zeros, and this is the internal state after 12 rounds of initialization. Okay. So currently it looks like we are doing things correctly, but I need to look at something else. As you can see, when you do the initialization, we did this part. We fed it with IV, key, and nonce. Then did the permutation 12 times. Then there is an XOR here. As you can see, it says 0 to the top is 64. And then concatenation with the key. This means that, okay, maybe I should also mention this. As you can see, it writes 128 here, 192 here. So recall that in a sponge construction, this part is called rate. This is capacity. So in this version, the rate is 128. As I mentioned, the initial version of Ascon actually supports 64-bit rate. So in the past, I implemented that. Now we are implementing the 128-bit version. So capacity is 192 bits, and our secret key is 128 bits. This is why it says that fill the first 64 bits with 0, then XOR the remaining 128 bits with the key. Actually, this simply saying that once go to initialization, we fill with these values, then we run the permutation 12 times. Now, XOR the last two rows, which is X3, with your key, and the last row with the remaining 64 bits of your key. Okay, so now we are done actually. So this is actually what is done before on the left side of this line, okay, this vertical line. So we have done the initialization, and you might see this kind of XORs also here, etc. This is called actually domain separation, because if we don't put it, somebody can take this and then put it here and create false forged tag for those values. Okay, so for instance, take this line and put it here. So this way they can mix the associated data and plain text part, etc. Okay, in order to separate these rows, by rows I mean initialization, associated data, plain text, we do something different at the end to make things different. So recall that associated data is the part where you feed your data, which is not going to be encrypted. As you can see, it is not encrypted here. We don't provide any ciphertext, but it affects the producing the tag at the end. So this part is optional. You may not have an associated data part. So for the sake of speed, I won't going to implement this, but it is, just assume that it doesn't exist for our case, but adding it will be very easy at the end, okay? Because we already did the hard part. We already implemented the permutation, and that's it, okay? So assume that I do the initialization. Actually, don't assume it. We already done it, but assume that there's no associated data part. Now we are going to encrypt some plain text and provide ciphertext, okay? Good. So let's just focus on a case where we have two blocks of plain text, and let's encrypt it and provide some ciphertext, okay? Okay, so assume that I have a plain text. It's 64 plain text of maybe 256 bits, because since each of them is 64 bit and I create 4 of them, so 4 times 64, it will be 256, which will end up being encrypting 2 blocks. Okay, so for the sake of clarity, I will simply initialize this to 0, this to 1, this to 2, this to 3. Of course, we can randomly generate it if we want at the end of the day. Okay, so assume that this is the plain text, and at the end, I will produce ciphertext Let's initialize it to 0 and see at the end if we really encrypt it, okay? So I did the initialization, right? Let's now do the encryption. Encryption now requires the internal state, right? Then the plain text. And I will also send the empty array cipher text, and it will return me these values, okay? But again, I don't have a function called encryption. As I mentioned, this is the style called declarative programming. I will go upwards and now define a function called encryption. And it will take the value that we wrote there. It's 64, x5. So actually, the plain text, can be very large. So I will not define its length here so that it will take as an input, as long as you want, and provide the put the ciphertext array. Okay, good. So at this point, the encryption function should know how many blocks I'm going to encrypt. So it will be actually half of this value, right? And you can actually determine it maybe. Okay, let me first printf this, which it calls how it's measured. So let's see how many bytes it claims. So I will save this and write size of plain text. Okay, and let's see what is the size of the plain text array. Okay, so let me run this. And it says 32 because there are 32 bytes here. Okay, so this has 32. And I need actually to divide it by 16 to see how many blocks I'm going to encrypt. So what I'm trying to say is for the encryption, you need to do this many block encryptions. Int e equals to 0, and e is less than this value divided by 16. And e plus plus, okay? So this is how many blocks that we are going to encrypt. And this number will be ended in 2, okay? Because we will encrypt 2 blocks, okay? So let's go to the picture back. So it does the following. First, XORs the plaintext 128-bit plaintext to the top of the internal state, which is rate is 128, right? So it does the following. X0 is XORed with PZ, we should say PI, okay? And X1 is XORed with PI plus 1. So since our variables are 64 bits, and we are actually XORing 128 bits, so instead of P, I should say plaintext, sorry. In order for this to be correct, I need to say 2 times I and 2 times I plus 1, right? Because in the first encryption, it will use plaintext 0 and plaintext 1. In the second encryption, it will use plaintext 2 and 3, 4 and 5, etc. Okay. By the way, my antivirus software thinks that I'm creating a virus because, recently there are many ransomware attacks where actually it does encryption inside. So this is why the executables I'm creating right now, the software, antivirus software thinks that I'm creating a virus. So this is why it gives an error. Okay, so but this is what I've done so far. I XORed with this, then I need to run the permutation 8 times. So at this point, ciphertext again 2 times I is actually the result of this XOR, which is X0. And the other one is +1 is this. Okay. So let me explain where we are. We are currently at this part. I XOR the plain text to X0 and X1, but also produces the output SC0. Okay. Now I have to apply the permutation 8 times. Luckily, we already implemented this. So what we are going to do is to call this, call this permutation 8 times. At the initialization, we called it 12 times. Now we are calling it 8 times. Okay. Let's go to the picture again. As you can see, now we are done. When everything ends, we will do the tag creation part. So, but we are currently at the plain text side. So let's do this. Then print the ciphertext. Okay. So less than 4. Of course, generally you will have more ciphertext pairs. So I will simply print a let's say I slash M. Okay, I will say print ciphertext. Okay, so maybe you will blank. And then finally print an empty line. Okay. So let me compile it. Okay, we received some errors. Apparently I did. Yeah, I haven't told him what to print actually. We'll print ciphertext I. Okay, let's recompile. Apparently I did other errors. Let's see. Yeah, I wrote this in a row. Okay, so how did we wrote it in the previous case? 0 on here. This was the correct version, I guess. Let me see. Yes. Okay. Apparently it doesn't work. As you can see, it says the ciphertext is all 0. So I made a mistake. This is the good thing. So let's go back and see where we are doing it wrong. Okay, so I call the encryption parts. I send X, plaintext, and ciphertext. So, okay, so size of plaintext here actually is not determined here. So this actually for loop never run. Good thing is that the compiler actually warns me. So this is the good thing. 10 years ago, compilers weren't this clever. So you have to try to find where your mistake was. So, I mean, if I cheat here and simply write 2 here, everything will work. But let's do this first. I mean, let's see. Oh, it didn't. Okay. Let me try to see. Okay, I forgot to raise the device in by 60. Now it should work. Let's see. Yeah, now we have 0 ciphertext. So I'm assuming, of course, everything else is correct, right? And being non-zero doesn't mean that I did everything correct, but currently it looks like it's correct. So this is how you encrypt it. Again, this 2 I wrote by myself because I knew that I was planning to encrypt 2 blocks, but maybe you can give it as an input to the encryption function, like here. So my previous thing was, we called it, I set size of plain text divided by 16, right? So let's say that this is print in blocks, let's say. Let's run it for blocks. Okay. Because it should be 2 now. So let me check if I'm thinking correctly. Yes, and the result is also the same. Okay. So I'm trying to parameterize this. So if you in the future want to include 4 blocks, I mean, I don't want you to write 4 here by hand. You know, it should work correctly. Okay, so we also done this part. So this part probably for the cases where it is not the size of the block. So, you know, in the past we talk about padding and etc. So at this point we don't need it. But again, this is kind of a domain separation parameter. If you are going to encrypt something that is not a multiple of 128 bits, then you should follow this line. But if it is multiple of this, then you know you should follow this line. This is what I understand from this picture, actually. Okay, so let's see what is. Yeah, I think L is that, right? I'm just assuming, but let's see. It should be explained someplace here. But you can also check it afterwards. Let me see if I can see the value L inside the text. Yes, this is the pad part, as you can see, right? Yes, this is where it explains if the final part is not divisible by this, then it follows the padding, etc. Okay, so I'm not going into detail for that. So let's go back to our picture because we have one thing left. That is the creation of the tag, the finalization part, right? So we need to do this. So let's do this. Now we have done the encryption. Finally, to simplify, if I do this, everything will fit on the screen correctly. Right? Let me zoom out a little bit. Now I will do finalization. So finalization also needs the input as our internal states. And I think nothing else, right? Good. So I will say, okay, yeah. Okay, so what I'm going to do is, maybe I should also write the tag as an array here. Tag, let's say, which is 128 bits. I will initialize it to 02. And I will send the parameter to this function. So our finalization function should take 2 input. But actually, we will also ignore the key. So I think I will also fill the key. But let me write this first. So with 64, x5, right? Then it's 64, tag 2. Okay. So what I was trying to tell it starts with XORing with the key, right? So top 128 bits, nothing happens there. But the below 192 bits, first 128 bits is XORed with the key. So maybe I should pass the key as a parameter, pass by reference, right? Key, okay. So I will also say bits 64 key. Okay. So what it says that first XOR X2 with key 0 and XOR X3 key 1. Okay, so this is our first step. Then it says perform ASCON permutation 12 times. This is the same as the initialization part, so I will simply go to initialization part and copy past this line. Okay. I'll simply write it here. Then I go back to picture and it says that last 2 rows XOR with the key again and produce as the tag. So this tells me that actually tag 0 is X3 XOR with key 0. Okay. Let me copy paste this. And tag 1 is the bottom row X4 XORed with the key. Now I will do the same thing as I printed ciphertext. Now I will print the tag. Okay. Since we do the finalization, let's say tag. Tag is just 108 bits. So it will be this. So let's see if the compile. Yeah, no errors for the compile. And this is the result. Okay. This is the ciphertext and this is the tag. So again, since I don't have any test vectors, maybe I did an error and I didn't notice it. So maybe since we are recording afterwards, we can watch the video and say that, okay, there was a mistake there. Okay. But important thing here, the declarative programming actually allows me to, think in a clear way to what to do. So for instance, I start saying that I will call the initialization function. Actually, at that point, I didn't have it, but then, I went up and implemented and follow these steps during the implementation phase. I'm trying to show this. If you do this like this, okay, actually the code becomes very simple. As you can see, we are at the line 67. When I give an homework to students to implement a cryptographic algorithm, generally I receive thousands of lines of code. But now I implemented an NIST standard with just 67. I can also, raise this line, 66 lines of code. Of course, you can, put this in a single line. I just wanted to show it in a clearer way. So let me, by the way, if you have observed any mistakes I did, just let me know. But I was just following this picture and I think I haven't forgotten anything. But what my implementation is missing the associated data, and it actually doesn't check if I need to do this padding or not. It simply assumes that, my blocks are directly fed here and, produced as the output. Okay. So I think this concludes our implementation. Okay, I stopped the